Alright chemists, let's talk through this new concept of galvanic cells. So we need to conduct investigations and measure and compare the reduction potential of galvanic half cells. What are they? Okay, let's lead you into there. So, we've learned that a redox reaction involves the transfer of electrons between two chemical species. And we started to talk about this displacement reaction, which I'm trying to show here. And I haven't labelled it well, okay? So we've got copper becoming copper 2 plus, or being oxidized in the presence of these silver ions, where the silver will coat the outside of the copper. It will precipitate out of reaction. So we'll get this spontaneous displacement reaction when we have these two conditions. What a galvanic cell is splitting these two half reactions apart from each other in space. Weird, okay? But we'll get you there, okay? So we've got these two half reactions, and all that's really doing is there's a transfer of electrons, okay? One way we can transfer electrons is to put them through a wire, okay? Electricity, okay? So here we're leading a bit more. So, as I've just said, copper, solid, and silver ions. Silver attracts electrons more than copper, so you'd get a displacement reaction. So here I've actually shown my silver being precipitated and my copper going to solution. And oh, good job, Mr. Roberts, putting a little blue to that solution there. So we get this when they're in contact, but we can get the same reaction when we separate them as well, and we connect them up into an electrical circuit. If all that's being transferred is electrons, we can set up an electrical circuit. So here we have what we call the electrical circuit of a displacement reaction, or a galvanic cell, okay? So here we've got our copper solid in a solution, and here we've got a silver solution that's not in contact with the copper. Physically, I should add. But electrically, through this electrode and through this wire and this globe and this voltmeter, coming down here to this wire, electrically they're connected. And I've got something else here, which we'll talk about soon, to complete a circuit. So we're getting a circuit of electrons or charges that move, and we still get the same reaction. So we're physically separating our two half reactions and running those electrons through a wire, and the benefit for this is electrons moving through a wire is electricity. We can get the electricity to do some work, or in everyday language, we can get it to do something for us, okay? So we can measure it with a voltmeter, and we can get it to turn on a light bulb, hopefully, if there's enough voltage. Okay, so here is the working galvanic cell, or our chemical circuit. We've got copper over this side, solid, and its electrons are being transferred through this wire this way over to this silver solid, which doesn't really matter. But the one that matters is this silver solution. We've got something metal connecting electrically to this silver ion here, okay? So the silver is coming out and precipitating on this electrode, and the copper is being oxidized and coming into solution. So this solution, maybe I should have done it blue like this one too, made it pretty. Okay, so that's a galvanic cell, a chemical redox reaction that's separated in space but connected electrically. We're harvesting those electrons moving between them. Let's see if it mentions anything more here. So here in my diagram, I've just generalized it. So over here, we're getting the oxidation reaction. We've got metal X, which is that electrode, going to X plus some electrons. The electrons are traveling over here. They're being consumed with the ions of Y and forming Y solid on the outside. Okay, so we've got this side is, we're going to label negative because the electrons are being repelled by it. And this side we're labeling positive because the electrons are being attracted to that side. So we've got a negative and a positive, just like a battery. Okay, let's read the words, see if there's anything new. A galvanic cell separates the reduction and oxidation reactions and connects them via metal wire in the aim of converting chemical energy into electrical energy. So pretty much, but what I said before, but converting chemical energy to electrical energy, perfect. Okay, two separated solutions containing electrolytes or ions in solution, each have an electrode sitting in them. A wire connects both electrodes, and this thing that connects them in between we're calling a salt bridge. It spans the distance between the solutions, and we'll talk about more of what makes a salt bridge work soon. And we form an electrical circuit. We form a single loop. Okay? Our negative end, where the electrons run away from, we call the anode. Like anion, negative, stuff like that. Okay? Our positive, where the electrons go to, we call the cathode, like cation. Okay? Also, this one here. Us chemists, we've got a good system for this one. We always, when we draw galvanic cells, we always, by convention, put the anode on the left and the cathode on the right. Okay? You can't always presume if you get a problem in an exam that it's going to be around the right way, and we'll be able to tell, but generally when you write your answers, please put the anode on the left and the cathode on the right. It's like a convention, like we write from left to right. All right. Okay, let's talk about the electrodes. So the electrodes are a solid substance that's electrically conductive. Otherwise you wouldn't get a circuit, okay? So the electrode may take part in the reaction. It also may not, okay? Now, the anode, the one on the left here, because it's being oxidized, electrons are coming away, okay? So the anode material may take part in the reaction, which we saw earlier, where it was the copper going into the solution. The other option is it may not take part in the reaction. It could be something else, and what we can do is we can get two different ion species. Okay, so imagine instead of it being a solid going to a plus aqueous, or imagine it being a plus aqueous going to a 2 plus aqueous. As long as oxidation is happening, okay, it doesn't really matter. Okay, so you can get oxidation from one ion to a higher oxidation state in the liquid, or you can get the metal being oxidized and going into solution too. So they're the two options for your anode. Can take part in the reaction, or it might not. It might just be there to conduct electrons. Okay, the cathode here on the right hand side cannot be chemically changed. Okay, if you have this as a metal, okay, on the cathode, electrons are coming in. Reduction happens at the cathode. You can't reduce a metal. You can't add electrons onto a metal. Okay, it doesn't work that way. Metals give up electrons. So the cathode can usually be any conductive material. Okay, so as I say here, it's often an inert material. So it's usually an inert metal because they conduct electrons really well. That can be plated upon. So you're hoping something will come out in a solution to be plated upon. Maybe. If you desire an electrode that doesn't take part in the reaction, there's 3 common examples. Okay, platinum. Now, platinum is, remember, it's one of our very unreactive metals. It really likes to hold on to its electrons. It's very inert, it's very unreactive. But the trouble with platinum is it's very rare and very expensive. Okay? Look at the other option, carbon. Carbon can conduct electrons. Okay? When it's in that hexagonal layer where the electrons lie above and below and they're delocalized, carbon can conduct electricity. So carbon is a nice cheap option, and that's the one that we tend to use if we want an inert electrode in our school lab because schools are poor. Anyway, look at the other option, gold. Okay, I don't think we're holding on to gold electrodes. Okay, so usually if you're asked in the exam, the more common ones to come up with, hey, we could use platinum, but if you're low on money, you could use carbon if you want an inert electrode. Okay, the electrolyte is a substance in solution or molten state that will transmit electrical current, or it contains ions, and those ions can move. Okay, that's an electrolyte. So electrolytes in galvanic cells may or may not take part in the reaction. Okay, the ion in the electrolyte may be the species that is getting oxidized or reduced, and you'll also have some in there that are spectator ions as well. So one of the main roles of the electrolytes on each side is to balance out the production of positive charges at the anode, to balance out, hey, we're pumping positive out here. We can't just do that. We need some negatives to balance it out. They're going to come from the other one. Okay, we need some negatives going that way. And because we're losing positives this way, we want positives to come back in and replace it. Okay, so we want to balance these charges. So electrolytes will commonly have ions. Nitrates are very common in them. And the reason why nitrates are common in these, because we want to keep these solutions going. Nitrates are always soluble, so if you're using nitrates in solution, you're not going to get precipitation reactions and lose your electrolytes, okay? Okay, onto this salt bridge thing. And this salt bridge I hinted below is going to help us transport ions, and that's its purpose. Its purpose is to transport ions back and forth between the two vessels, okay, to be part of that electrolyte solution and to complete the circuit. So if we're getting if we're getting positives here, what we're going to do is transfer negatives over to here. Okay, and if we're losing positives over here, we're going to get spectator ions that are positive coming over to replace it. So that's the job of a salt bridge, is to transport ions. Okay. Now, when we make them in the school lab, what we're going to do is we're going to get a piece of filter paper, really holds onto the water, and what we're going to do is soak it in a solution of potassium nitrate. So it has some good old potassium plus that can float back and forth, and nitrates that can float back and forth. Now soak it in that, and we're going to span it across 2 beakers. Okay. The other common thing, and we will try to do it, it's a bit more difficult to do, is to use a YouTube, not a YouTube video, but an actual tube that it looks like a test tube in a U shape. And what you can do is fill that with a solution and bridge it across. Okay. So that's actually what a YouTube is rather than the website. Okay, and in that YouTube we put in the electrolyte solution, so it can travel back and forth through that tube. Without the salt bridge, the circuit wouldn't be complete. You haven't got a complete circuit where the ions where the charges can move freely. So we break the circuit doesn't work. Okay, so without that salt bridge, we're not getting a voltage on our voltmeter on the wire, and we're not getting our bulb lit up if we can do that. So here's a nice summary slide that you can take a look at. I've kind of summarized it with a diagram, given a table if you like tables, and using some acronyms, if that's the right word, down here. All right. Oh, I've got this a bit late, but I thought I'd add it here. There's an alternate method for calculating this total cell voltage, or the total cell voltage for your reaction here. And here's the reaction down here, okay? Notice it's very similar to the one that we used before. It's still got reduction and oxidation in the same spot, but there's a positive between them. And why does it do that? Okay, the alternate method is to find your reduction half. Say you've got silver. We usually do silver with copper, don't we? So let's highlight them both. I think I might do this on the next slide though. Oh yeah, I do. So it's using this positive one and adding to them, okay? Now you can use whichever method, they're mathematically reliable, but some people find this easier, okay? So it's plus instead. Let's talk through an example because you'll see what I mean, okay? So copper and silver, let's find them, okay? So I've highlighted them here, silver and there's copper, okay? Since silver has the most positive, it's being reduced, and copper's being oxidized, okay? Okay, since the oxidation, what we're going to do, since the silver has more positive reduction potential, it will be reduced while copper is oxidized, or we're doing the reverse reaction as what's on the reduction table there. So what we do there is we keep the silver the same way, and we flip around the oxidation half, and we change signs on the oxidation half, or the upper one, okay? So instead of being positive 0.34 like on our redox table, or sorry, on our reduction table, it's now negative 0.34 because we're going in the opposite direction, okay? Now what we do is then we put it in this positive equation, and so we're getting the positive 0.840 and our plus, our negative, our new voltage for the reverse one, okay? And then we're still getting positive 4.6 volts, okay? Well, the benefits for this method, you don't need to remember around which way the redox and the reduction and oxidation go around with the equation, okay? So even if you put the potential for the oxidation half before the reduction half, you're still going to get the right example, okay? So that's the benefit. But I really like the negative one because it goes with the word red minus ox, okay? But that's another method if you choose to use it. All right, so working galvanic cells are spontaneous, okay? So connecting up any metal and electrolyte mixture will not guarantee a reaction. You can get non-spontaneous examples. Only those spontaneous will work or give a working galvanic cell, okay? And the way you can test it is you can wire in a voltmeter, you can put a bulb in there, okay? So only spontaneous reactions will transfer electrons, and so you'll see a voltmeter, I was going to say go up, then you'll see a positive value on your voltmeter, or you could have it wired around the wrong way and have a negative, but you'll see a reading on your voltmeter, and you'll see the bulb maybe light up, okay? So that will occur when the total cell voltage is positive. When you've got a negative cell potential, you won't see a negative value when you wire in your voltmeter and your light. What you'll see is 0 volts and no current running through the bulb, okay? You won't see a negative voltage. A negative voltage, remember, in practice is you've got the wires around the wrong way, flip them around, okay? Okay, adding on here, because sometimes we get talked about this table and oxidants and reductants, okay? So here I've just changed the language. We're still going from oxidized to our reduced, okay? But here I've started using oxidants and reductants, okay? So our potassium is the most reactive, and our most reactive going the opposite way to being oxidized. So it's our strongest reductant, okay? Because it's more likely to be oxidized. Our fluorine here is our strongest oxidant, okay? It's being reduced, and it's more likely to be reduced. It's got the most positive half voltage, so it is our strongest oxidant, okay? So the reduced species over here are going to be our reductants, okay? So we've got our strongest reductants down to our weakest reductants down the bottom. Fluoride really likes being fluoride. And the other side, we've got our weakest oxidant. Our potassium plus really doesn't want to do anything. It's happy where it is, so it's our weakest oxidant. And our strongest oxidant is our fluorine, okay? We don't often come across fluorine because it's quite reactive, but you'll see here, and we'll talk all throughout this course about the permanganate ion and the dichromate ion. We come across those in solutions and salts all the time, okay? They're the most handiest things that we can use to oxidize something else. So when we come across in Year 12 where we want to oxidize an alcohol or do something like that, we'll be talking about, let's bring out the permanganate and let's bring out the dichromate. Okay, we've got a couple of different types of galvanic cells that you may get a question about, and I just thought I'd add them in there. Here's what I've taught you is a galvanic cell. That's only one type of galvanic cell, and it's sometimes referred to a simple galvanic cell. Okay, so that's your go-to, what you think about. You can also make a galvanic cell in a U-tube. Okay, so we talked about that before. You can actually make one in the U-tube, and here's one that's using a copper electrode and an inert platinum electrode, but we're pumping in gas there. Okay, so what have I said here? Therefore, a salt bridge is not needed. So an inert electrode, platinum or copper, is dipping into a solution containing both an oxidized and reduced form of one of the elements. Okay. So here we've got chlorine going to chloride. Okay. So it's also possible to bubble a gas into there. Please don't bubble chlorine glass. You'll die. Purely theoretical question. Another thing that I thought I'd add that's come up in past HSCs before and past yearlies is this cell notation, or a way that we write and express a cell simplified. Okay, so it's a shorthand, and this is what I'm talking about. This is cell notation. What it's telling me is I've got two things, and it's orientated in the same anode to cathode way. Okay, so it's saying here at the anode, you've got X solid going to X2 plus, or you've got the oxidation of X. And I like to think of this two lines as the salt bridge. And on the cathode side, you've got from left to right Y plus being reduced to just single Y. Okay, so that's another way we can write and give a simplified expression of a galvanic cell. So for our example of our copper-silver galvanic cell here, what's happening at the anode? Well, oxidation's happening at the anode, and we've got copper 2 plus going to copper going to copper 2 plus. So copper and that line, and then copper 2 plus. And then we have the double line that I like to think of as the salt bridge. Oh, actually, you can think about it as a wire and a salt bridge. And at the cathode, we've got silver plus being reduced to silver solid. Okay, so cathode, anode. Okay, comes across sometimes in questions. Let's do a couple of examples. We've got 3 examples there. Let's do it. Draw a diagram of a working galvanic cell, or a spontaneous galvanic cell, between the metals zinc and copper. Okay, let's find them on the table to see which way around we'll get a working galvanic cell. So we need zinc is there. So it's negative 0.76. And copper, I'm assuming they mean copper 2 plus. Just assume that. There it is. Okay, so out of the two, copper has the more positive. So it's going to go in the forward direction, or it's going to be reduced. Zinc has the more negative, so it's going to go in the opposite direction or be oxidized. Okay? So, let's draw our beakers. Terrible beakers. Okay. So here I'm going to have some electrode. I'll put a voltmeter. I might put a globe in there if you want to. And we're going to have some other electrode. I'm going to draw thinly in there my solution. Okay, so at our anode on our left, we're going to get electrons coming away and going this way in our diagram. So a loss of electron is oxidation. So our oxidation is going to happen here. So we're going to get zinc solid going to zinc 2 plus. Okay, so this electrode is going to be zinc solid, and it's going to come out of solution and go into zinc 2 plus. All right. Electrons are going to travel through. They're going to come down here. So that's our negative anode, and here's our positive cathode. They're going to be attracted to this, and we're going to have our reduction happen here. So we're going to have copper 2 plus, and 2 electrons go to copper solid. So we need in our solution copper 2 plus, or we're going to have like something like copper sulfate in there. It's going to come and it's going to plate our electrode here. So we don't actually need a copper cathode here. We can, but all it's going to do is transmit electricity. It doesn't need to be copper. It could be platinum. It could be any metal. any metal or carbon, okay? Alright, it doesn't need to be the copper because we're putting copper onto it. It just needs to transmit electricity in this case, okay? Our anode needed to be zinc though because it needed to be the material that we're putting in solution. Here, copper will plate any of those. If you put platinum in there, copper will plate it. If you put anything that wouldn't change the reaction, so put platinum or carbon in there. Not really any metal because you could screw the reaction up. We'll talk more about that soon. Okay, I'm missing my salt bridge. Okay, so there is my anode reaction, and there is my cathode. I think I got everything labelled. Okay, what voltage will it produce? Here's our formula. The reduction half minus the oxidation half, redox. So it's going to be 0.34 volts from over here minus negative 0.76. Alright. Put it in your calculator, 1.10 volts, which is greater than 0. And so that's reassuring that it's spontaneous. So it actually worked how we designed it to be. Okay, let's do the same thing, but now let's talk about aqueous iodine. Here's our iodine, I2 aqueous, so we're talking about this reaction. And aluminium, I'm thinking it'll be higher up. Here we go. The more positive one will be the reduction half. So our iodine is going to iodide. So that's our reduction. And our more negative will be our oxidation half. So it's going to go in the reverse. So aluminium solid to aluminium 3+. Okay. 2 beakers. Terrible beakers. We've got our anode on the left. We've got a cathode on the right. So our positive on the right, our negative up there. Electrode, wire. I'll put a voltmeter in there. My second electrode will be there, dodgily. Our solutions, our salt bridge, our electrons, we draw it so they travel this way. They go from negative to positive. Okay. Oh, one thing that I should bring up here, it's a good point. Remember that current, or the flow of electrons, was talked about before electrons were discovered. So arbitrarily, one of those famous old electricity guys said, current runs from positive to negative. But since we've found electrons, we know that electrons are the negative things that move from negative to positive. So if you ever get a question talking about current goes the opposite way to electrons. So I might just add that in here. I should add that on a slide or something, just in case. So current goes in the opposite direction, positive to negative, because physicists couldn't change their mind. But it's okay. Anyway, distraction. So we've got our anode, we've got our general setup. We need to decide reduction. Okay. Reduction consumes, so reduction happens at the cathode. So aluminium being oxidized, or aluminium producing electrons, needs to happen here. So we need an aluminium solid electrode that gives off electrodes and turns into aluminium 3+ in solution. And so here we're taking iodine. Oh, I forgot the 2. Oh, I'm scrolling. Sorry, guys. I2 aqueous. And it's going to, in solution, iodide. So our whole reduction equation's happening in solution. So our electrode can't take place in the reaction. So platinum or carbon. Okay? And it's just transferring the electrons over to the iodines in solution and turning them into iodides in solution. Alright. Our salt bridge is there too. Let's go into a bit more detail. Let's not go into too much more. Positives and negatives will be going back and forth. So because we're producing positives on the left-hand side, negatives will be going that way. And because we're gaining negatives over this right-hand side, we all must gain positives to balance it out. So we'll be transferring negatives and positives that way. Let's talk about the voltage. So it equals the reduction half minus the oxidation half, which equals 0.62 volts is there, minus this one up here, negative 1.68, equals 0.62 plus 1.68, 2.30, don't forget the 0, volts. Okay, so it's positive, that's good, we've set it up the right way. I was just jogging my memory there. Sometimes you'll have questions that ask for the largest cell, which combination will produce the largest cell voltage. Remember, if they're close together but around the right way, little cell voltage. If they're very far apart in the table and they're around the right way, large voltage, a large punch for your buck. You're gonna light up some bulbs and stuff like that. Okay, past HSC example. Let's do this before the end of the video. Here we've got a galvanic cell in the diagram. Let's take a look. We've got nickel on one side and copper solid on the other. Have they done it the right way? Okay, it's up to us to figure it out. They could have the cathode on the left and the anode on the right. Okay, but we've got nickel and copper. So let's go back to our table up here. Let's use this one. Let's rub it out and find nickel and copper and find out which way it's going to go, because they could be trying to trick us and do it around the wrong way. So it is copper going to, let's presume copper 2 plus. So we've got this reaction here. And where's our nickel? Is here. Okay. So for it to spontaneously work, we're going to need the more positive going is reduction, and the more negative is oxidation. Okay, so nickel's being oxidized. Okay, that's good. So we've got nickel solid going to nickel 2 plus 2 electrons, and copper's being reduced. Okay, so copper 2 plus 2 electrons going to copper solid. Okay, have they got it around the right way? Okay. Oxidation happens at the anode, or our nickel will go to nickel 2 plus. So they've got it around the right way. That's helpful, but it's always worth a check. One day they're going to do one where they don't put it around the right way, and they're going to try and trick you. And so here we've got copper 2 plus going to copper solid. Okay, and they're using an electrode, copper electrode. So calculate the potential difference. Okay. So our reduction minus our oxidation. Our reduction is copper 0.34 minus our nickel negative 0.24. So that's 0.58 volts, isn't it? Don't need my calculator for that. Watch me do an error and make a fool of myself. So 0.58 volts. Include a net ionic equation for the overall reaction. Oh, well, I've almost got it here. Luckily, I went back and read the equation. 2 electrons being given and 2 taken, so we don't need to multiply. Nickel solid plus copper 2 plus going to nickel 2 plus copper solid. All right. We've calculated the cell potential, and we're including a net ionic for the overall reaction. Good. After a period of time, a solid deposit is formed on the copper electrode. Well, that's good. Copper will form on the copper electrode, we decided. And it was dried and removed and had a mass of 0.395. Did we do this problem somewhere else? Calculate the final mass of the nickel electrode. Oh, that's a good one. Okay. So we gained 0.395 grams of copper solid. Let's find out how many moles that is. So 0.395 grams divided by the molar mass of copper, 63.55 grams per mole. 6.21 times 10 to the negative 3 moles of copper formed. So the nickel must have lost 6.21 times 10 to the negative 3 moles, because it's a 1-to-1 ratio between them. Okay? The initial electrode mass, okay, so let's find out. I reckon it's better to go, it must have lost a mass of, okay, so our moles times it by a molar mass of nickel, 58.69. So it must have lost 0.364 grams. Okay, so the final mass, 10.27 grams minus 0.364 grams. Okay, two decimal places is 9.91 grams. Okay. The final concentration of the nickel 2 nitrate solution. Alright. So if we gained 6.21 moles of copper solid, we must have also gained the same amount of moles of nickel 2 plus. So we yep, okay. So we can work out how many moles we had initially. Gonna run out of room, aren't I? And it's messy, I'm sorry. Is going to equal our moles of nickel nitrate is 0.100 mole per litre times it by our volume in litres is 0.2000 litres. Okay, 0.1 times 0.2, 0.02, isn't it? 0.02 mole. And we must have lost the 6.21 times 10 to the negative 3 moles. So final moles equals 0.01379. And the concentration, it is, I'm assuming, in the same volume. So the concentration of nickel 2 plus equals 0.01379 moles on 200 mil, 0.2 litres, 0.06895 mole per litre. How many sig figs? 3, 4, 3. So I could probably do it to 3. 0.068990 3 sig figs. That's very messy and I apologise. Okay. You can now do this worksheet and we've got a practical to do. And that's it for content for the chapter. There's a few practice questions that you can do. But that's all the theory. Alright, catch you next chapter.